Ladies and gentlemen, welcome back to the Simpkins Physics Corner. It's Mr. Simpkins with some Week 15 Projectiles Part 2 for Physics Academic. So my students, make sure you download this packet. You can find it right at the top of your module for our week this week. And this is our launch lesson. So I want to walk you guys through. Last week we were discovering the big ideas behind projectiles. All right, and as we looked at those big ideas behind the projectiles, we were taking a look at a couple of things. Like, for example, for the horizontal motion of a projectile, the horizontal motion is constant. And in the vertical motion of a projectile, the motion is going to be accelerated. And so if I pull up your module right here, it says 12.7 to 12.11 Projectiles Part 2. Download this packet, and it'll look just like this. We went over this problem for individual practice last week, so what I want to do this morning is go over a few questions with you to outline these big ideas that we saw last week. Remember this big phrase, T is key. And what that means is that time is the great unifier between X and Y motions. Let's look at the problem that we already completed together, for example. In this one, we see Mrs. Rolls, poor Mrs. Rolls, again, thrown off the building because her students are sick of worksheets. I do not endorse this activity, nor did I write this question, just for a disclaimer there. But as we see this, what's happening is you're going to be moving horizontally, right, because you're going to be traveling at a constant speed horizontally, but at the same time you're doing that, simultaneously, at the same time you're doing that, you're also falling, and you're falling a greater distance every second, of course. And when you string those two together, when you string together the constant motion in the horizontal direction and the accelerated motion in the vertical direction, what you get is this parabolic shape, or this parabola. And the big idea that we went over last week is that the motions of X and Y, horizontal and vertical, for a projectile are independent. Let's see if I can spell it right today. Not sure, because I ain't an English teacher. Plus simultaneous. And simultaneous means at the same time. So the X and Y motions, I'm moving horizontally and dropping at the same time, simultaneous, but the gravity, the force of gravity doesn't care how fast I'm moving horizontally, nor is my horizontal speed affected by that pull of gravity. All right? The force of gravity doesn't change when I'm doing side to side. So they happen independent but simultaneous. Just as a side note, I had a student ask me about this the other day. Air resistance isn't a thing. I mean, it is a thing, but we never account for it in our problems because we need calculus to do that, and I don't feel like teaching you calculus. So that's just a little side note. We usually say air resistance is negligible, or in the context of our labs, we use a small steel ball bearing. It's dense and it's small, so that means it doesn't, it's not slowed down by air resistance that much. Let's look at some examples here for how to set up and use this XYT table strategy. All right, so here's the first one. An arrow is shot horizontally at a velocity of 30 meters per second off a cliff that is 50 meters tall. So I'm going to label and draw a picture. That's always the first step that you want to do. Label, draw a picture. It's going to shoot off the cliff there. Okay, that's a really tall cliff, by the way. Find how long it takes the arrow to reach the bottom of the cliff. Now, this question is cueing you to find time, but remember, T is key. So after you draw your picture and label it, the next thing you want to do is this X, Y, T table. And look at this magic. Isn't this magical? Look at this. X and Y are independent. See how there's a wall between them? But they're simultaneous because a T connects them together. Oh my goodness, that's a beautiful thing. Now, 30 meters per second is your horizontal speed, so I'll call that Vx, and of course that would go on the X side because it's your horizontal speed. 50 meters is the height, and Y is how high, so I'm going to use the variable Y to represent vertical position or height as 50 meters. Now this may look a little sparse, right? We don't have a whole lot to go with on this one. However, we always know that projectiles are under the influence of the force of gravity. And if that's the case, then we know that this G, this acceleration due to gravity, or sometimes we call it gravitational acceleration, we know that value is 9.8 meters per second squared. So, steps, underline the numbers. Draw the picture with the numbers on it. Draw your XYT table to organize stuff. The next step is always solve for time. And to do that, you have to evaluate which side do we know more about, the X side or the Y side? Well, in this case, we know more about the Y side. And if you go to your physics, your handy-dandy equation sheet, ding, then you will find the free fall equations. Now, depending on what class you're coming from, the equations might look different. I give my students a little hack equation. T equals the square root of 2y over g. That's the time it takes to fall from rest. Now, just as a side note, if you're not in my class, this comes from the big kinematic equation, which is, oh gosh, who wants to write this whole thing out? VIT plus 1/2 AT squared. Okay, and it comes from that equation. But if we assume that our our final height is 0, because that's the ground, and our initial height is 0 because we dropped it, then you can see how not too long to get to t equals square root of 2y over a. And since our acceleration is g, I just plug in a g there. So that's the short version of where that came from if you're not coming from my class and you're watching this video. And if you do, give it a like, hit the subscribe button, and leave a comment. That'd be fantastic. So let's go ahead and find the time it takes to fall. 2 times 50 times 9.8. All right, and we grab our handy-dandy calculator. Don't come to physics class without your calculator, folks. And we're going to do the square root of 2 times 50 divided by 9.8, and that's going to be 3.19 seconds. So, part A, how long does it take the arrow to reach the bottom of the cliff? 3.9 seconds. Now, what I'm going to do here is just give you a little idea. The time it takes to fall, we just calculated, is 3.19 seconds. Well, guess what? As it's falling, it's also moving horizontally. So that amount of time is the same amount of time it takes to move side to side. Independent, but simultaneous. There it is. And only for a horizontal projectile, right? All bets are off if I shoot this thing up in the air at an angle. Okay, we'll get to that later. But if it's a horizontal projectile, then the time it takes to fall is equal to the time it takes to travel out. And we can do this. We can take the time, t is key, and we can move it over to the other side of our XYT table. Now the question says find the range of the arrow. Just a little side note, that means x, how far did it go, the range. And so delta x is going to be Vx times t. Where does that come from? Well, we know velocity is displacement over time from one of our basic definitions from chapter 2. And if I algebraically solve that for delta x, the range, that's what you get. So if I plug this in to finish this one up, I'd get 30 meters per second times 3.19 seconds, and that would get me an answer. All right, if you want to know what it is, you got to bring your calculator. No, I'll get it for you here, just for the sake of time. The range, or how far we would go, is 95.7 meters. All right, so there's one sample of how this might look. Let's go to the range. Range safety is important, but the range is a fun place, especially for physics. A rifle is carefully aimed and fired at a target 50 meters away. All right, so here's our little physics pew-pew. Pew! And it's going to go over here, and it's going to drop a little bit, right? When you're sighting in a scope, and whether you're a hunter out there, I like to show Meat Eater. He's going like, he's trying to shoot like mountain goats that are like 1,000 meters away or 1,000 yards away. It's crazy stuff. You have to adjust for that force of gravity pulling the projectile down. So you got to carefully aim it, and it looks like in this case our target is 50 meters away. And the bullet hits the target. Here's a little bullseye guy. All right, the bullet hits the target 1 centimeter below the center. All right, so there it is. Find how long it takes the bullet to reach the target. So we did our picture. We labeled it. I didn't leave myself a lot of space for my XYT table, did I? Let me scroll down a little bit. All right, so let's do our XYT table. X, Y, T. Okay, so the X, the horizontal displacement here is 50 meters, and the Y is, now I know you're tempted to write 1, but don't do that. If you go to McDonald's and you buy something and you pay with some cash and your change is 1 cent, that's what it's going to show up as the cash register, right? Okay, so 1 centimeter, or 1 centimeter, is equal to, you got to swing the decimal 2 places over, is equal to 0.01 meters. All right, so 0.01 meters, just like at McDonald's, you would get $0.01 in the form of an Abe Lincoln, a penny. All right, so this is actually going to be 0.01 meters for the height. In this case, the wide distance that you dropped, our bullet dropped there. All right, now, the first thing after, so we got the, we pulled our information, drew our picture, labeled the picture, got the XYT table. Next thing is to solve for time. Always solve for t first. Now, let's not forget our old friend g here. G is 9.8 meters per second squared. Now, technically, it's negative. It's going down, but whatever. And so we want to find time first, which is square root of 2y over g. So let's do that. T equals square root of 2 times 0.01 over 9.8. Now, as you can imagine, this is going to be a very small amount of time. Guys, it's a bullet. Okay, they go fast. You know, Superman faster than a speeding bullet. Well, that's because it's going fast. So if we take the square root of that, that is hardly any time at all. That is 0.045. And I'm keeping so many decimals because, you know, we got to have some meaning in our number here. So that's how long it takes the bullet to reach the target. Not very long at all, which means it probably hasn't fallen very far. In fact, we know it hasn't. Here's what I want to know. If that's the case, how fast is that bullet going then? It's obviously going really fast if it gets there that quickly. So what we can do, again, only because it's a horizontal projectile. If I shoot this thing up in the air at an angle, all bets are off, okay? But for horizontal projectiles only, the time in the y direction is equal to the time in the x direction, so 0.045 seconds. The time it takes to fall, to drop that 1 centimeter, is the same amount of time it takes to travel horizontally to reach the target. And so with these two pieces of information, and it asks us for what is the horizontal velocity of the bullet, we could use our equation for velocity, displacement over time. So let's do that. 50 meters divided by 0.045 seconds. Now, if you know anything about math, you know that when you divide by something really tiny, you get a really big number, which is okay. It makes sense. Oh, good Lord, that is insane. 1,111 meters per second. I don't know that that's realistic. I got to check my box to see if that's a realistic feet per second velocity you could calculate, I guess. Oh, yeah, actually, let's do that real quick. About divided by 3. All right, that's a reasonable velocity for meters per second. So that is a second example. Now we have a couple minutes left. Let's see if we can get one more in here. Yeah, we'll do this one here. All right. A toy car rolls off the table. I'll draw it up here for you. Rolls off the table with a speed of 2.2 meters per second. All right, if the table is 0.8 meters tall, how long does it take the car to hit the floor, and how far from the edge of the table does it land? All right, so we drew our picture, underlined our knowns, XYT table. I'm going to hit the gas a little bit since you guys have seen a few of these. So our Vx is 2.2 meters per second, and our Y is 0.8 meters. And, I got to write equals Y if I want to be a good physicist. And then, of course, we know our G. And so in this case, we know more about the Y direction than we do the X direction. Therefore, we're going to solve for time in the Y direction. Square root of 2y over G. Give me a second here. The countertop side, how long does it take? Yeah, I was looking for a different type. If you want to see a sample of how you solve for time with the other direction, there aren't any. I should have given you one of those. Just a little side note. Sometimes you will use the X direction information to solve for time with this equation. T equals, let me make sure I got it right. If velocity is x over t, then t equals x over x velocity. All right, so if you just kind of, I had you guys put that in your notes last week, but make sure you're aware of that equation. That would be used if you know the velocity and you know the horizontal distance and you want to find how long it's taking. So that's just a little side note for you guys there. That'd be helpful. 2 times 0.8 meters divided by 9.8, and we get the time it takes to hit the floor. It's only going 0.8 meters down, so it's not going to take a whole lot of time. Let's see how long it does take. 0.404 seconds. Okay, and remember, the time it takes to travel in the Y direction, if it's not going up in the air or shot down, if it's exactly horizontal velocity, then the time in the Y is equal to the time in the X. We can move this puppy over here. And then, of course, we could get our how far away is it. So X equals Vx times T. All right, again, that comes from here, solving for X. And you can plug those numbers in. So Vx 2.2 times T of 0.404. That's going to get you a little 0.888, repeat, meters. That's how far out you go. Kind of cool. So with the little bit of time we have left, let me outline what I'd like you to do for me today. We do have one more there. But what I want you to do as far as your assignment goes is complete the week 15 launch HPM, which stands for Horizontal Projectile Motion Problem. If you're looking in Canvas, it looks like this, week 15 launch HPM problem. Click on that. You're going to download the problem right here. And please, in order to receive full credit, make sure you draw your picture like we did today. Make sure you use an XYT picture or a table like we did today. Show every step of your work like we did today. And circle or box your final answer like we did today. Please turn this in, and it will close at the end of this week, so please do so in a timely fashion. Before I send you off here for today to try out a few of these on your own, let's go ahead and do a recap. For a projectile, like that, what is it doing in the X direction as far as acceleration? Well, it has no acceleration because there's no horizontal force. Unless you're one of those, what about the force of air resistance? Yeah, good luck with that. No, I mean, that is a legit thing to consider, but we don't consider it in these types of problems because I don't want to do calculus for physics, and I don't think you do either. Let me go back to the top here. Hold on a sec. That's not going to work. All right, there we go. Horizontal velocity is constant because, again, there's no unbalanced force in the horizontal direction. There's no reason to accelerate, so I got to make constant velocity. The most common equations we use, Vx equals delta x over t. And then we can rearrange that a little bit for delta x equals Vx times t. And we can also see t equals delta x over Vx. So those are the kind of pocket of equations we have. Acceleration for vertical is negative 9.8 meters per second squared, or 9.8. And its initial vertical velocity is 0. And I'm going to run out of time, so I'll see you next time.